So let's take a look at the first types of scenarios, and that being improper integrals over infinite intervals. The infinite intervals here simply tell us that we're going to from some finite number to positive infinity or negative infinity to some finite number, or the situation here that has both negative and positive infinity as our upper and lower bounds. So in the scenario where we're going to go from some real number to infinity, all we're going to do is go from a to, and I'm going to take this infinity and I'm going to make it a b. So now I'm going from a to b, but I'm going to take the limit as b goes to infinity. And that limit is what allows us to actually go ahead and find the value of the integral. So we would integrate this using a to b, and literally if a was 2, b would be b. And I would integrate it just like that, and then at the end take the limit of whatever I end up with as b goes to infinity. Now this other scenario is if I start at negative infinity and go to some value b. Well, I'm going to do the exact same thing as I did number 1, except I'm going to replace negative infinity with a, go ahead and integrate it like normal, but take the limit as a goes to negative infinity. And then this last scenario, I have a situation where I'm going from negative infinity to infinity. So what I need to do is pick a c, so that c is actually a real number anywhere, just some real number. 0 kind of comes to mind because that usually makes life easier. But there may be other values that would make life easier. But what I'm going to do is break up the integral into 2. First, I go from negative infinity to c, and then c to infinity. And then to actually integrate these two, I would use these two techniques up there. So I would combine technique number 1 and 2 in order to complete the integral from number 3. So let's take a look at an example. Here we go. I'm going from 1 to infinity of 1 over x dx. So what I'm going to actually work with is the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. See, now I'm going to integrate this like normal, but I'm going to keep this limit. I'm not going to drop it. So I need the limit as b goes to infinity of, well, the integral of 1 over x is ln x. So this would be ln x evaluated from 1 to b, which equals the limit as b goes to infinity of ln b minus ln 1. Now notice the limit only applies here. You know, if I wanted to bring it over here, I could, but it wouldn't make any sense because there are no b's here. Ln 1 is simply ln 1. If I had a b in here, then I would have to take the limit as b goes to infinity. So as b goes to infinity, ln b will go to infinity, and ln 1 is 0, so infinity minus 0, well, obviously that's just infinite. Therefore, I'm going to say this limit, or this integral, doesn't exist, d and e. Well, rather than d and e, I'm going to bring in some new terminology here. What I'm going to say is that the integral is unbounded, or a better term would be to say that it is divergent. Divergent means that it goes to infinity. I have or negative infinity. If I integrated this and I had negative infinity as a solution, that would be divergent. If I had a real number as a solution, then I would say that it is bounded and it is actually convergent. Let's take a look at this integral now. I want to go from 1 to infinity of 1 over x squared. Now we saw that 1 over x gave me an infinite amount of area under the curve, so what's going to happen with 1 over x squared? Well, this process will be the exact same thing that I just did. This is going to be equal to the limit as b goes to infinity of the integral from 1 to b of x to negative 2 dx. So this will be equal to the limit as b goes to infinity of, I can take the antiderivative now. That's why I wrote it like this. The power rule is all set up now. So this is going to be a x to negative 1 over negative 1, which obviously, evaluate from 1 to b, which obviously I'm going to rewrite as the limit as b goes to infinity of, I'm going to pull this negative out front here and just make it 1 over x from 1 to b. Let's not lose track of this negative there. So this is going to be equal to, here's my negative, the limit as b goes to infinity of 1 over b minus 1 over 1. Well, as b goes to infinity, this will go to 0. So this will give me a negative 1, but I have a double negative, so this will just be 1. So the area under the curve between 1 and infinity of 1 over x squared is actually equal to 1, whereas the area under the curve from 1 to infinity of 1 over x is actually infinite. What that brings up, and we'll get into it later in the course, if you look at the graphs of these, here's 1, here's 1. If this is 1 over x, you know it goes like that. 1 over x squared will also start here, but it goes to 0 faster. Both of them asymptotically go to 0. But what this is actually saying is that there is a finite amount of area between this curve and the x-axis as I go to infinity. It's 1. But what I ended up with is an infinite amount here between these two curves. And that's what made it blow up and give me infinity here. So we'll explore this in much more detail later in the course. But the key here is not that it simply goes to 0, that asymptotically it goes to 0, but rather how quickly it goes to 0. 1 over x squared goes to 0 fast enough. 1 over x does not.